Hello everyone, my name is Jiyuan Wang. Today I'm going to present HeteroGen, which automatically generates HLS-C code based on an original C code. The emergent data and compute-intensive software applications are increasingly constructed to leverage heterogeneous architectures. A heterogeneous application refers to a software application that consists of both host code and kernel code, and can offload its compute-intensive kernel from CPU to FPGA for acceleration. Such architecture is becoming widely available to industry, such as AWS EC2 F1 instance. There has been HLS that raises the programming abstraction levels to C language. However, programming such heterogeneous application with HLS, especially for FPGA, has been a long pain. It is because HLS programming is not standard C programming. It requires strict resource finitization and compile time because we are synthesizing hardware which cannot be changed at the runtime. Based on C program, developers must remove all the dynamic language features before compilation and synthesis. Developers will also have to insert pragmas or directives to expose hardware synthesis details and further optimize the code based on hardware knowledge, such as HLS programming involves a significant amount of manual rewriting effort in transforming C to HLS code. Unlike C programming that we have ready-to-use refactoring, testing, debugging, optimization tools, yet no effective developer productivity tools to aid the manual transformation process for the programmers. With those difficulties in mind, how can we make this development process accessible for general developers? To develop a heterogeneous application with HLS, the state-of-the-art approach in industry is to profile the original C program and identify the performance bottleneck. For example, by running this Qian program with Xilinx HLS profiling libraries, we find that 80% of the execution time was used for calculating the L2 norm. This function will be identified as a kernel function, which can be offloaded to FPGA. Then HLS experts will understand this code, manually rewrite this kernel function to HLS compatible code. After 7 minutes compilation of the entire application and 10 minutes CPU and FPGA code simulation, she finds that the HLS version behaves identically with the original version. Next, she may want to check the real performance on hardware, which requires a 2.5 hours FPGA synthesis. This process will repeat until all the requirements are satisfied, and she finally gets 7 times speed up for this L2 norm on FPGA. But porting a C program to HLS version has to address some unique difficulties. Here are some examples. HLS requires specifying bit width for each data type. Instead of using default 32 bits on CPU, HLS uses arbitrary bit width. For example, one can use 7-bit integers for her program. Similarly, we need to tune the procession of floating point numbers. Like instead of using default 8-bit exponent and 23-bit mantissa for 32 float points, developers have the flexibility of tuning procession for memory saving. Additionally, all kinds of HLS compilers require strict resource finitization before compilation. Because we are generating a standalone hardware which cannot be changed at the runtime. But at the software level, we have so many dynamic language features and application behavior. As a consequence, developers have to manually remove all kinds of dynamic data structure. If you ever attempted to port these tens of lines of standard C code to FPGAs, you will be frustrated to see full compilation errors, which will never happen in C. For example, you will see nested pointers are not supported. Dynamic memory usage, such as malloc or free in standard C, is not available either. Pointer operations are restricted. There's no way of comparing a pointer is null or not. And all the recursive functions will not compile. So developers have to manually repair those compilation errors to make it synthesizable. In software engineering, there have been search-based program repair techniques to fix errors since 2008. A repair technique is usually equipped with a set of adversary code edit pattern and an oracle, and it iteratively applies random code edits to a buggy program and evaluates the new variants with testing oracle as a fitness function. If automated program repair was so successful, why can't we use it to fix the previous compatibility errors in C so that it becomes HLS code? Well, this is not straightforward. Since we are adding the code, each newly generated variant will have to compile and execute it. Then we can see there is a highly overlooked assumption here. The program must be compiled and executed in the order of milliseconds. For example, a well-developed toy, Qian Prog, from University of Michigan, reports 0.2 seconds for each child. However, HLS for our previous example will take 40 minutes for compilation and simulations. Another challenge is that each time we fix an error, we absolutely do not want to alert the semantic of the previous program. For example, we delete every code line will definitely remove all the errors. For the purpose of semantic preservation, can we formally verify the equivalence like traditional compilers do? Unfortunately, there's no easy way to build such a validating compiler between C and HLS-C, because all dynamic and unbounded data structure must be finitized to static size implementation. So the programs before and after transformation are naturally different. Currently, the only way to check equivalence is to execute both versions with concrete test inputs. We address these challenges in HeteroGen. With the help of generated tests, we first build an initial version of the customized data bitwidth. Next, the initial version will be compiled using an HLS compiler, guided by all compilation error message. It explores applicable edits with some technique to speed up the search process and output the final HLS version. With this in mind, the fundamental question here is what would be the code edits? Our observation is that HLS repairs have patterns. For example, different applications with recursion can be fixed by the same edits of transforming recursions to Stark-based implementations. So we did an error study based on Xilinx online website with 1,000 posts, which is like Stack Overflow website, but is specifically for this community. We concluded 6 HLS compatibility errors, and for each type, we extracted a couple of code edit patterns. Those patterns are represented using parameterized AST edits to be assigned to a given context. For example, we can use this edit to make a Stark whose size will be assigned to A1. Apparently, I believe every one of us will have the experience that one error can have multiple fixes and can also involve multiple edits. We also observed that HLS repair require dependent edits. For example, the key problem of this example program is the usage of recursions. We will have to replace it with a Stark. But before this transformation, we find that its arguments are using pointer based on dynamic memory usage. Then another required edit is to replace this dynamic memory usage, such as malloc and free, with a static array-based implementation. Inspired by Miryung's work at UCLA, to encode complicated code edits with basic edits. We record the dependency relations based on our error study, such that for each error type, we will have a set of code edits pattern and then relation graphs like this one. Then the next question becomes how to do the repair and search based on those graphs faster. We use a two-fold optimization to speed up this process. This early candidate rejection is used to terminate the compilation process early if a repair does not conform to HLS coding style, such as one primitive like HLS unroll for loop does not appear within a loop body. We can safely terminate the compilation because it is absolutely a waste of time to do so. By doing that, for the uncompilable code, we can reduce the time from 40 minutes to 1 second without LLVM front-end checking without invoking the subsequent compilation. We'll also leverage a dependency-guided search space pruning process. In a typical search-based repair process, the edits are usually applied randomly in each iteration. As we have constructed the dependency graph for each error type, we can use this error-specific dependency structure to enumerate the space of applicable repairs. For example, it can be 1, 1, 2, 1, 3, or 1 to 5. Our insight is that using dependency relation can significantly reduce the number of search iterations because those iterations can provide clear guidance on which edits to choose next rather than try out edits randomly. HeteroGen successfully generated HLS compatible version. Some of the programs may not outperform the manually optimized programs. As an example, the manually reported face detection program that comes with this open source subject from the kernel contains over 3,000 line edits. Such edits utilize a trace-based memory banking technique for hardware optimization. HeteroGen currently does not have such hardware-specific optimization including edits, but our search-based repair has been improved to be successful in the legacy code rewriting, and it automates up to 432 lines of code edits, reducing HLS rewriting effort. We also conclude an arbitrary study to evaluate the speedup from each of our two search optimizations in isolation. The baseline of this study is to downgrade our tool to contain only either early rejection or dependency-based search. We show that the work clock time spent to find out same repair edits and the percentage to actually full compilation invocations. And we conclude that the dependency-based search and early rejection respectively contribute to 35 times and 4 times speedup. To summarize, HeteroGen successfully produced an HLS compatible version for subjects that we are using in a 3-hour time budget. It automates the edits of 438 lines of code, and our dependency-based search achieves 35 times speedup compared against a random search process. And the generated tests cover more than 97% of the branches. To summarize, HeteroGen automatically translates C and C++ code to HLS code by search-based code repair process. HeteroGen speeds up the repair process with 2 optimizations. First, apply code edits with dependency to reduce the search space. And second, the style check to avoid unnecessary compilation process. HeteroGen issues the correctness of translation code by automatically generate test input. We release our HeteroGen on GitHub. Besides HeteroGen, we also develop a set of tools to help software developers to use IPJ For example, we propose HeteroRefactor, which automatically refacts achieve performance improvement and resource saving for FPGA program. And HeteroFast, which is a fuzzing tool specially designed for FPGA program and achieves 754 times faster in exposing the same set of distinct platform portability errors than naive fuzzing. If you are interested, please check out our GitHub for more information. Thanks for listening.